Hello everyone, this is Dilleswara Rao. I'm from my Aeronautical department. I'm taking classes on automatic control of aircraft undergraduate course. So last few classes we are discussing on control surface systems and how to control the objects and all. We have been discussing on that. So this is about control system. Control system, control augmentation system. Like previously, we discussed on stability augmentation system. So that stability augmentation system that is discussing about how to make that airplane to stability condition when it is going to unstable condition, and automatically how that control surfaces are being adjusted to make them into controlling environment. So that was happened. That was discussed on the last few classes. So now we will see what is control augmentation system. Like what is the things involved in this control augmentation system. Also, we will discuss. So this will be as it is like if you see. This is like if you compare with stability augmentation system also, there will be two parts of lectures will come with this one. So that will be like in stability augmentation system, if you see in last class, so we discussed on the pitch acceleration control system, acceleration assay system, and lateral and directional assay system also we have discussed at that time. So as usual, here also in the control augmentation system, that pitch acceleration system and lateral and directional CAS system also we will discuss now. So just going to the topic. So the like SAS system only, that when an aircraft is under manual condition, so that stability augmentation system of preceding sections are like previous sections are mostly discussing on the automatic flight control system requirement only. But in case of high performance military aircraft, like you see in last classes, there was a caution we have given, like for a military aircraft with higher altitudes and higher pitch rate controls are required. That time, SA system alone is not recommended. So SA system alone not recommended means, that means what? Actually, SA system is talking about make that aircraft to a stable condition only. While we are going in unstable condition also, automatically that system adjusts that aircraft to come into that stable condition. So likewise, here also in the control augmentation system, this is also making that control surfaces to adjust automatically in a stable condition only. So if you see, for a military from a high performance aircraft like military jets and fighter jets, so when pilot may have maneuver the aircraft to its performance limits and perform tasks such as precision taking of targets, specialized CS are needed. Like for a high performance aircraft, these high performing target, the specialized targets and weapon releasing agents also required. But in case of flight control technology is being advanced for nowadays. So it will provide the pilot to selectable task tailored control laws. For example, if you see, although the role of a fighter aircraft has to change include launching missiles from long range and important classical dogflight dogflight conditions also required. Like while because military aircraft may not be like a single mission profile, so it will have a many in between controlling agents. Controlling agents means in between piloting things also required, because sudden pull up, sudden pull down, and rapid turn up, rapid turn outs, and rapid pitching down and pitching up. Those things also is required. this may not be this may not be continued with regular systems. So there will be a special systems are required for controlling this agents also. So the dog flight places premium high maneuverability and agility, that is ability to change maneuvers quickly and rapidly, and aircraft control system that allows the pilot to take advantages of this maneuverability only. So in this situation, the suitable controlled variable for pitch axis is normal acceleration of aircraft. So this is the component of acceleration in negative direction of the body axis, like a z axis only. So it is directly relevant to the performing maximum rate turn, and must be controllable up to that structural limit of the airframe or pilot's physical limits only. Because sudden pull up or sudden pull down, sudden turnouts are required in mission profile. So that time we may not control that aircraft very rapidly. So that is why we need to make that controlling agent should be react very precisely. So for that condition only we have augmented this system also, like control system augmentation system only we have installed here. So that dog flight, like a G command control system is an appropriate mode of operation. So the other reasons for type of the system will be see it on coming things. So another common mode of operation is that pitch axis control augmentation only. Like pitch axis system means what? When it is when an aircraft is suddenly increasing its pitch up or pitch down moment according to the z-axis, like you see, I think you know that aircraft axis system also we have already discussed. So this is axis related to x-axis related to linear motion. This is y related to that pitching moment, and z related to moving up and down moment only, like yawing moment. But that movements like a pitching moment with respect to z-axis will be like positive z. This will be like a positive z and this is a negative z. So with respect to that direction, like a positive z movement and the negative z movement, there are high maneuverability conditions are involved on this. So for that condition, how to augment that systems related to control the aircraft is been very essential thing need to see here. So that, like a pitch axis augmentation system and pitch command system so are been installed. So when a situation requires a precise taking of a target, that means sighting the device, it has been found that deadbeat response to that pitch rate commands as well suited to the task. So that controlling of pitch rate is also a preferred system for approaching and landing. So the systems have been designed like see in reference tolls 1985, um, which have been blend together to together the control of pitch rate and the normal acceleration. So with respect to that lateral and directional control, the most prevalent control augmentation system is roll rate command system, and this may be designed to roll the aircraft around its own velocity vector rather than the body axis. So here this may not as I said earlier, so there will be like a pitch augmentation system and roll like a directional augmentation system. In a both way, how these control systems have been augmented to make it that aircraft to controlling in a stable condition. So that only we'll see. So see here, first one we are talking about pitch rate control augmentation system. So here you see the block diagram of pitch rate augmentation system. So you see that system from previous classes also, if you find the system is having input signal will be there. So that signal will be summing up here. This is called a summing amplifier. So like this is so this is a summing amplifier. So so here you see the Here you see the system amplifier system that has been given here, that input signal, and this is we are having a summing amplifier. From that summing amplifier, that integrated circuit is been there. So from that integrated circuit, local summing amplifier also there. From here, that automatic feedback system coming out from the control systems also been connected to this summing amplifier. So from this summing amplifier, that actuator control integrator, like here the pitch rate integrator, and this roll rate integrator also been installed here. So from this, the signal will be transmitted to that aircraft actuators. From there, it will be given to that control surface. So from here, the output signal will be given to that control surface, like maybe that elevator or flaps, or maybe ailerons, or maybe radar, like that. So here you see that this is like a type 0 control system that is not very satisfactory, because the control inputs to that plant may be quite large, like several degrees of elevator deflection is installed on that. So while the gains in the error channel may not be usually very high, so and entire large control errors have been installed with, I mean, coming with a type 0 system. So therefore, there is an upgradation with that one is given here. So the proportional plus integral compensation of is being used to provide the more precise control. So inner loop alpha feedback is being used here. Like see here, that inner loop alpha feedback is there here. So this is the gain rate. Filter feedback system, and that means noise filter and error filter feedback system, and alpha rate feedback system is been given here. So this feedback system is again summing up here, so that with that feedback system only, that input signal is being controlled, and that has been given to that actuators. So the proportional part of PI compensator can be replaced by an equivalent inner loop pitch rate feedback. So that is given here, that pitch rate feedback thing. So that has been shown as a dotted line only. So this is a equivalent pitch rate feedback system only. So this is a pitch rate feedback system. So uh, this leaves the closed loop poles unchanged, but removes the PI from 0 from the closed loop transfer function, thus reducing the step response of overshoot. So it will be shown to convenient to keep the PI 0 while performing the root locus design also. So the design of pitch rate CAS will now can be explained later in with examples also, like that. That will be coming on next classes, like that the significance of CAS system. At that time, we will explain with practical application of this thing also. And normal acceleration control system, augmentation system. So in a fighter aircraft, if an accelerometer is being placed close to that pilot station, like for a sudden increasing of velocity, we need to use this accelerometers also. Like this accelerometer is also like a device which will control the engine speed, and that nozzle speed also, I mean nozzle flow rate also, it will be increased, and that turbine speed also will be monitored with these accelerometers only. So actually this about these accelerometers we already discussed in previous classes, like accelerometers and sensors. If you find how what type of accelerometers and sensors are installed in every aircraft, so you can see that. So that the theoretical background behind that is been explained here only. So for an aircraft, accelerometer is placed close to the pilot station, aligned with the body jet axis, and being used to feedback sensor for controlling the elevator. So when the pilot has a precise control over the jet axis load during a high maneuver, because when high maneuvers are required, there should be a precise monitoring should be there on Z-axis control system. So if 1G is subtracted from auxiliary input, so in terms of G means what? That in terms of acceleration. So 1G, 2G means we are making against to that gravity, how much acceleration we are taking against to gravity, because aircraft is flying in air means it is flying against to the gravity only. So if it is taking that pitch up motion, so it is taking against like a sudden pitch up or sudden pull up is required. So that means a sudden increasing of altitude is being making up. Like see here. So when an aircraft is being flying at this maybe some altitude, so this is some altitude, suddenly it needs to pitch up means, so it may be that pitching rate need to be upside. So here the altitude may be changed, so that jet movement only we are attaining here. So that means this is the x direction, this is the z direction. If you see, so the jet movement increasing only, more is there in aircraft pitching up. So for that here that maybe here 1G acceleration is being employed. So if it is increased to 2G or 3G, like sudden pull up is required, so that means that acceleration need to be given to that aircraft to making it to pitch rate higher. So that 1G is subtracted from accelerometer output, and the control system will hold the aircraft approximately in level flight with no control input from the pilot. If the pilot blocks the out from a G load and relaxes any forces in the control sticks, the aircraft will turn to 1G flight. So other useful features of this system are that the accelerometer output that contains a component proportional to alpha and can be inherently stabilized in unstable short period mode. So and the accelerometer is an internal sensor, so that is less noisy and more reliable than an alpha sensor. So here noise means it is not like a maybe that acoustic noise, like sound noise may not be there. So there will be like a reception means signal transmission noise only. So if anything signal lost is there in between transferring the signal from one place to another, like one device to another device. So if there is any external signals have been disturbing that one, so that noise filters also will be that is we will talk it as a noise only. So that noise filters also been installed here to make that signal more precise to give that good reception. So the acceleration at the point P, that is at pilot station, is related to that acceleration at another fixed point in the rigid aircraft frame. So that may be controlled with equation you see here. So AP by I. So API P stands for the pilot station will be equal to ACM I plus omega B into R P by CM plus omega B by I into omega B by I into R P by CM. So this is giving things related to that accelerometer controlling only. So here RPCM is the accelerometer position vector from with centimeters. Like that position means, because when we are that acceleration is given to the object means for sudden increase in velocity, that means with the sudden increase in velocity that position change will be rapidly will happen. So when the position change is rapidly happening, so how that position changing have been given, that will be making it as a in terms of values. So that has been given with this R only, that positioning vector values. And the accelerometer, if aircraft in longitudinal axis and aligned parallel to that z axis, So that positive up normal for a positive up normal acceleration will be given, that AN stand for normal acceleration. So that normal acceleration will be identically equal to minus AP I prime z, that will be equal to minus AP, I mean minus A square Cm by I minus phi by minus q into xa plus pr xa. So here that z stands for z axis, I mean z component values. So and that XA is FRD exposition. That means FRD exposition of the accelerometer. In wings level up, level up or pull up only, the first two terms of the right hand side are non-zero only. So in turning flight, the next subsection shows that a fighter aircraft control system that would be designed to roll the aircraft around the stability axis, and then PR equal to P2 tan alpha. Therefore, if aircraft is rolled rapidly at a high alpha, like high alpha means high angle of attack, the PR term will be quite large, and the position range will be quite large, and that contributes negatively to the normal acceleration, as the aircraft nose moves along a circular arc. That means the circular arc means when if it is that nose movement is going straight, means it's like a straight line way. But if it is taking that arc way, means there is a more turn rate it is taking. So in a real aircraft, the specified force sensed by the aircraft accelerometer can be given by that AN will be equal to Fn plus minus GD and ED cos theta cos alpha. So here NZ is NZ will be equal to AN by GD. That is normal acceleration in G units, like for acceleration in the ratio. G by GD is very close to unity only, like that G by GD is your unity. Then that NZ is almost equal to Fn minus cos theta cos phi. These all entire things will be depends on G units only. Like in terms of G, like 1G, 2G values only we will give. So here theta and phi will be that roll rate and that pitch rate only, the pitch angles. So in level flight, small angles of attack for feedback signal of a control system can be mostly, like for small angles, like theta is 0.01 or 1 degree or 2 degree values. So for that, that cos theta cos phi will be almost 1 only, will be equal to 1, because cos 0 equal to 1. So if it is increasing to other values also, uh, uh, other values also will be identically 1. So that means that NZ is almost equal to Fn minus 1. That Fn will be that force in normal direction. So the normal acceleration is approximately 0 in steady level flight, if and often called incremental normal acceleration. So that equation is included in non-linear aircraft model. That numerical linearization will be yield with a linear equation for an perturbation term in term its non-zero steady level flight value. A linear equation can also be obtained algebraically by finding the increment in aerodynamics and thrust force related to the perturbations in state and control variables, and this involves the jet variables, that jet derivatives. We can see it in further things. So for the nonlinear F-16 model, numerically linearized for a level flight condition. So that the table will be there after this one. So here that for a normal level flight condition, that AN will be equal to 0.00399 VT plus 15.88 alpha plus 1.448 Q plus 0.03 delta E. So here alpha, Q and delta E are in degrees only. That alpha is pitch rate, alpha is angle of attack, Q is pitch rate, and delta is the elevator angle of attack. So here These quantities will be defined with respect to longitudinal aerodynamics derivatives only, and the elevated deflection which produce aerodynamic forces directly acting on this acceleration. So the AN is very insensitive to the pitch altitude when theta is very small. So that elevated to normal acceleration transfer function can be make it from the Jacobian matrix solution. So that is been given here, that AN by delta E. So that is normal acceleration to the elevator angle of attack, elevator angle input function only. So that is been given here. So this is the transfer function that has been used for making that accelerometer comfortably. So the transfer function has been same folds where because NMP is 0 at s equal to 13.14. Like if you see that root locus values for these s values, that means that Laplace transform at Laplace uh, transformer value, that is s equal to 13.14 is there, then the normal acceleration responds to negative step elevator command, that will be initial negative acceleration quickly followed to that positive normal acceleration. The physical explanation of NMP behavior is that when an elevator control surface is deflected, that trailing edge upwind to the upwind to produce the positive normal acceleration. This creates a downward increment of forces for the tail. Like when that control surface is deflected, trailing edge upward, if the control surface is produced upward, so there will be a positive normal acceleration. So the normal acceleration will be positive only, like suddenly that pitch that altitude will be increased. This creates a downward increment force of a downward increment of force in the tail. Like when it is going like that, so that I mean, if it is pitching up is there, so that there will be a downward force on the tail. So that normal forces will be acting on tail directly in normal direction only. So the result is that CG of aircraft may be dropped nominally during the pitch up. So the normal acceleration may be briefly become the negative before build up its positively. So at the autopilot, I mean the pilot station ahead, that's the CG. The normal acceleration also depends on the pitch angular acceleration about the CG only. So the the positive normal acceleration may be felt in a pitch up that has been given on table 1. If you see here that values for XA for a different Laplace operator values. So that has been given here. The zero, I mean, here you see that elevator to normal acceleration transfer function is from 0 to a range of accelerometer positions from the CG forward. The zeros close to the origin do not change significantly from the positions, and only that static loop sensitivity and remaining zeros are being shown. So that table shows that acceleration positions is being moved forward to NMP value 0 values, that will be towards infinity, and the static loop sensitivity will be decreased, thus keeping the transfer function DC gain state. So eventually the static loop sensitivity changes the sign, and the zero comes from infinity along with negative real axis. Finally, combining with the other non-zero values also will be complex and flat. So at the position near to 6.1 feet forward to the CG, and NMP effect disappears, and this point corresponds to an instantaneous center of rotation when an elevator input is suddenly applied. So that means when elevator input is suddenly applied, so there will be a sudden increase of I mean sudden increase of altitude, and that rotation, yeah, the center of rotation also may be changed. So that see uh, the table for a static loop for sensitivity normal accelerometer positions for a positions like that XA is been increasing from 0 to 15 feet. If it is been increasing slightly with the values, how that sensitivity values have been given here, that has been shown here. So for a F-16 aircraft, if you see it on a previous condition, the pilot station is approximately 15 feet ahead the CG point, and therefore not close to the instantaneous center of rotation. So inevitably, the design of a normal acceleration control system to achieve the good handling qualities is difficult and can require a good deal with refinement based flight test result only. So a control system that has been good a normal acceleration step response may have a pitch rate response with very large overshoot, and conversely the pitch rate overshoot may lead to sluggish normal acceleration response. Like when a pitch rate is overshoot means what? When we are giving one signal to get one attained value, but it is getting more than that attained value. Like 1g, we need to take 1g value of acceleration, but when we are giving that signal, it is taking a 2g value. That means it is being the values are overshooted only. Like overshooted means here the values are not in control only. So that type of acceleration responses with respect to that positioning things also may occur with this one. So that C star criterion is an appropriate for initial evaluation of control system. So it is based on normal acceleration of the pilot's condition only. So ultimately we can say, like, for an accelerometer in an internal within the fuselage sensor, the higher reliability and the lower noise than the external alpha sensor. Like external alpha sensor is been we said no in the SAS system, that alpha center is like a external sensor that has been given on that aircraft wing section, that will sense the aircraft bending and the noise filter noise section also, turbulent sudden turbulent things also, it has been sensed and giving that signal to that controlling agent. So however, these both accelerometers and alpha sensors are typically employed in modern flight aircraft, and this reduces the dependence on alpha sensor only solely. Like when we are, in the alpha sensors in the SAS system, we said that we have a sensing agent that will gives you information about that wing bending, sudden bending due to that sudden loads and gust loads acting on that wing, and with sudden increase in pitching, how that the bending need to be avoided for different values of pitch up rate, and for a directional stability, for a sudden turnout positive direction and negative direction, how that noise filtering and this structural reliability also depend upon this sensing agent only. So for that reason, we have given that external alpha sensor has been given, installed in the outer surface only. So, but in modern aircraft, with that, in addition to that alpha sensor also, there will be an internal internal accelerometer sensor also is being installed within the fuselage only for getting that acceleration in a stable condition. So there will be some disadvantages is there with this acceleration feedback, is that the gain of the transfer function varies widely with dynamic pressure. So accelerometer noise may become a problem also. So if low dynamic pressure, the gain has to be greatly boosted to achieve a desired closure loop response, because we said that pitch rate and elevator values are very less, so that more solely depend on that FN only. That acceleration, normal acceleration has been equally almost equal to FN values only. So when this dynamic pressure is being installing, when this dynamic pressure is sensitive, when when a, that normal forces are more, that means when the pitching up rates are more, so that that accelerometer values also will be going to beyond the up to that defined value, so that the controlling agents will be precisely operate. But for low dynamic pressure values, like low dynamic pressure values means almost in steady flight, or maybe with a gradual increasing on pitch, or maybe with a gradual increasing on accelerometer, so that the dynamic pressure values are maybe very less. So that time that gain scheduling, like a gain response maybe need to be boosted. Like need to be boosted means that the input signal need to be increased more, so that closed loop function, because if that closed loop function need to be operate mean that input signal also need to be strengthened. Otherwise we can't operate that device fully. Like you see in a low voltage system, how that motor has been I mean how motor will be operated for a low voltage. In a low voltage things, a motor cannot be operated with full-fledged force. There will be I mean sometimes it won't start also. That means there will be a minimum range of voltage is required to run that motor. So like that, here also, to complete the closed loop sensor operation, so there will be some minimum forces are required to operate that system also. So that is why that low dynamic pressure values of these CAS systems are one of the drawbacks getting from this only. So however, the control system augmentation and stability augmentation system, that sensors like alpha sensor, external alpha sensor, and this roll rate sensor, and this pitch rate accelerometer sensors also, everything is installed in a modern aircraft to make that aircraft to more stable. Because if it is going to unstable condition also, automatically these sensors will give the information to pilot, or if pilot unable to make them into stable condition, the sensor can operate, like a sensor can alter the operation in unstable condition and make them into that stable condition only. So this is all about pitch rate augmentation system. And next class we will see that lateral augmentation, lateral control, lateral augmentation system, for a control augmentation system, like a lateral and directional feedback systems also we will see it on the next class. So for your reference, you can refer this textbook. So if you have any further doubts, you can clarify by commenting your questions below this video. So that's all about this CAS system part one. So next class we will see it on lateral directional movements. So thank you.
Like, share and subscribe. Hit the bell icon for more updates.